This is video number 7 on electric charges and fields. Timestamps are given in the description box. You can watch parts of video if you are running short of time. In this video, I will talk about motion of a charged particle in an electric field which is uniform. I will discuss one conceptual question and 2 questions from JEE Advanced PYQs. Finally, I will summarize this video. Motion of a charged particle in an electric field. So this is a charged particle which is negatively charged. For example, this could be an electron. This is entering a region of a uniform electric field. The electric field is in the direction from positive plate to the negative plate. X-axis is towards right and y-axis is upwards. And since the charge particle is negative, the force on it will be in the direction opposite to the electric field. So the force on the negative charge particle will be downwards in the direction opposite to the electric field. So this charge particle will get deflected downwards. So initially the charge particle has got velocity in the x direction and there is no force in the x direction. So it will continue to move in the x direction because of this velocity. But in the y direction, there is a downward force because of the electric field and it will start moving in the y direction. So this particle has got both x and y motion. We can analyze the x and y motions individually and we can combine them. In the x direction, there is no acceleration because the electric field is in the vertical direction. So what is the initial velocity in the x direction that will continue to remain at all instants of time. The displacement in the x direction is the constant velocity vi into the time t. In the y direction, there is a force due to the electric field, and since the charge particle is negative, the direction of force is opposite to the direction of the electric field. So the direction of force will be the negative y direction, and its value is e into e. So the acceleration because of this force is the force divided by the mass, and the negative sign indicates the fact the direction of the acceleration is downward. Using v equal to u plus at in the y direction, we get vy equal to the initial velocity in the y direction. Initially, the particle, when it enters this electric field region, has got only horizontal component of the velocity. There is no vertical component of the velocity. So initial velocity in the vertical direction is 0 plus at and ay into t, and acceleration in the y direction is force by mass e by m into t, and we can use s equal to ut plus half at square in the y direction. S is y, and initial velocity in the y direction is 0, and half at square, we have acceleration in the y direction as e by m. So from this we get y as minus half e by m into t square. So as time increases, x will increase linearly and y will go as t square. So at any instant of time, if you want to get x and y, we can use these two formulas, and we can also relate x and y at a given time instant. So we can eliminate t from equations 1 and 2 to get how x and y are related. So from the first equation, we can get the time as x by vi, that we can use in the second equation as y equal to minus half e by m. In t square, we have x by vi square. So this is how x and y of the charge particle are related. So we can see that the path is parabola, and since the coefficient of x square is negative, it's an inverted parabola. So this is an inverted parabola in the xy plane. So this is same as a projectile motion of a mass under the influence of Earth's gravity. The time of flight and the maximum height reached by this charged particle can be calculated in the same way as it was done for the projectile motion, which was studied earlier in class 11 physics. Let's consider the question. An electron is projected as in figure with kinetic energy k at an angle theta equal to 45 degrees between two charged plates. The magnitude of electric field so that the electron just fails to strike the upper plate should be greater than. You can pause and attempt this question. This is an electron, so it will experience a force in the direction opposite to the electric field. So the direction of force on the electron will be downwards because electric field is upwards. So the electron which is projected, it can go either like this or it can go and hit the plate. So if the electric field is strong, it will take this path. If the electric field is weak, it will go and hit the plate. But for one particular value of electric field, it will just go and touch this plate and come back. So electric field is low means it is this path, and electric field is high means this path. For one particular value of electric field, it will just go and touch this plate and come back. So value of electric field which is higher than this value corresponding to this path, it will not touch the plate. So you have to find the electric field corresponding to this path. So for this path, the maximum height that is attained by the projectile motion is the distance between the plates, which is d. So the kinetic of the particle will have two components, the vertical component and the horizontal component. Vertical component is because of the vertical velocity. The components of initial velocity are u cos 45 in the horizontal direction and u sin 45 in the vertical direction. Cos 45 and sin 45 are same. So the kinetic energy will get split equally in vertical motion and horizontal motion. And if the total kinetic energy is k, then the kinetic energy of the individual components will be k by 2 and k by 2. This is initially at this point. At the maximum height point, the vertical velocity will decrease to 0. It's a turning point. So the vertical kinetic energy will reduce to 0. But the horizontal kinetic energy, it will remain constant because the horizontal velocity is constant because there is no force in the horizontal direction. The horizontal motion is a uniform velocity motion. There is acceleration only in the vertical direction. So the kinetic at this maximum point is because the horizontal component, which is k by 2, which remains unchanged from the initial value. So there is a loss of kinetic energy from the initial value to the maximum height point. So this loss in kinetic energy will go in work done by the electron in moving against this electric field. Electric field try to pull this electron down, but this electron is doing work to go from here to here. That much amount of work done will come at the expense of loss of kinetic energy. So this work done is f dot ds integral. So that is f into ds into cos theta, and ds cos theta is, we can think as the displacement along the direction of the force. So since this force is uniform, it will come out the integral sign, so it will become f into component of displacement along the direction of electric field. So when the charge particle moves from here to this maximum height point, the displacement in the direction of electric field is d. So work done is q into d. From this we get the expression for electric field as half k divided by qd. So the correct option is option C. Here we have neglected gravity because the mass of the electron is very, very small. So the gravity force acting on this electron is very small compared to the electrical force because of the electric field. This is the next question. This is from JEE Advanced 2020. An uniform electric field E equal to minus 400 root 3 y cap Newton per coulomb is applied in a region. A charged particle of mass m carrying positive charge q is projected in this region with initial speed 2 root 10 into 10 raised to 6 meter per second. This particle is aimed to hit a target T, which is 5 meter away from its entry point into the field as shown schematically in the figure. Take Q by M as 10 raised to 10 coulomb per kg. Then, four options are given. The particle will hit T if projected at an angle 45 from horizontal, will hit T if projected either at an angle 30 or 60 degrees from the horizontal. Time taken by the particle to hit T could be root 5 by 6 microsecond as well as root 5 by 2 microsecond. Option D, time taken by the particle to hit T is root 5 by 3 microsecond. So this is more than one correct option. You can pause and attempt this question. So since this charged particle has to go and hit this target, it means that the path of the particle should be like this. That means that the range of this projectile motion should be 5 meters. If it is more than 5 meters means it will go and sit somewhere farther away, like this. And if it is less than 5 meters, means it will hit somewhere here. So for the charged particle to hit this target T, that means that the range of the motion should be phi. And the range is given as the horizontal component of the velocity, that is u cos theta, into the flight time, the amount of time taken to go from here to the target T. This is a standard way of solving projectile motion. So the range is phi. And to get the flight time, we'll analyze this vertical motion from this initial point to the maximum height point. So between these two, if we write this v equal to u plus at, at this point the vertical velocity is 0. So v is 0, the initial velocity u sine theta, plus a into time is the half the flight time. From here to here, the target it's okay. The maximum height point is this of this path. So half the flight time is to go from here to this maximum height point. So it's half the flight time. So from this you get the flight time as minus 2u sine theta by a. So using this expression for flight time, in this one, we get phi equal to u cos theta into minus 2u sine theta by a. So simplifying, we get this one. So this is a standard formula for relating the range of the projectile motion to the initial velocity and the angle theta. So if you remember this formula, you can straightaway use this formula. So using this value for u is 2 into root 10 into 10 raised to 6. So squaring that will give 4 into 10 raised to 13. And acceleration is QE by m. Q by m is given as 10 raised to 10. And then the electric field is minus 400 root 3. So that minus will cancel this minus, will become 400 root 3, 10 raised to 10 into sine 2 theta. So everything is known here except for the angle theta. So from this we get sine 2 theta is root 3 by 2. So that means 2 theta is 60 or 120 degrees. Sine theta is positive in the first quadrant and also the second quadrant. So that means 2 theta is 60 or 120. We have to take both angles. So that means theta is 30 or 60 degrees. So option B says the particle hit T if angle is 30 or 60. So option B is true. Option A is not correct. Now we get the time of flight. So once we know the angle theta, we can use this thing to get the flight time. So in this, if you put the value of u as 2 root 10 into 10 raised to 6, and then A as 10 raised to 10, from this we can get A as 10 raised to 10 into the electric field 400 root 3. And sine theta values sine 30 or sine 60, so it's half or root 3 by 2. Two possibilities are there. So simplifying, we get the flight time as root 5 by 6 microsecond or root 5 by 2 microsecond. So option C says the time taken is root 5 by 6 microsecond or root 5 by 2 micro. So option C is correct. Option D is not true. So the correct options are B and C. This is the next question. The figure below depicts two situations in which two infinitely long static line charges of constant positive line charge density lambda are kept parallel to each other. In the resulting electric field, point charges Q and minus Q are kept in equilibrium between them. The point charges are confined to move in x direction only. If they are given a small displacement about the equilibrium positions, then correct statement is R. So it's multiple, more than one correct option. Option A, both charges execute simple harmonic motion. B, both will continue moving in the direction of the displacement. Option C, plus Q executes SHM while minus Q continues moving in the direction of displacement. Option D, minus Q executes SHM while plus Q continues moving in the direction of the displacement. You can pause and attempt this question. This is actually a simple question, but you have to use a result. The direction, the magnitude of the electric field due to infinite line charges lambda by 2 epsilon naught into 1 by r, where r is the distance from the wire and the direction of the electric field is radially outward from the wire. So at this point, where plus Q is kept in the middle of these two, let the electric field due to this first wire 1 be E1 And let's assume plus Q is positive. It's not given in the question, but let's assume Q is positive. So E1 will be in this direction, it will be a repulsive force. And because of 2 also, there will be a repulsive force in this direction. And since this lambda is same and it's equidistant from both 1 and 2, the magnitude of electric field E1 and E2 will be same, but the directions are opposite. So the net electric field at this point is 0. So the force acting on plus Q is Q into the net electric field. So it will be 0. So this position is as equivalent position. And then we have to figure out whether this is stable equivalent position or not. So to find that, we have to give a small displacement. Suppose we displace this positive charge in this positive direction by a small amount, then the electric field due to 1, since the distance has increased, it will go down, decrease a little bit, and electric field due to 2, since it's going close to 2, it will increase. So because of this, there will be a net, since E2 is more, then there will be a net force acting towards left. So when there is a small displacement towards right, there is a restoring force which will bring it back to its original position. So similarly, if we displace this thing towards left, then it's going closer to 1. So the amount of electric field due to 1 will increase. So E1 will increase and E2 will decrease because it's moving away from 2. So this means that there will be a net force towards right. So this force is a restoring force which will bring back this plus Q to this original position. So this charge particle, if you give us small displacement along the x direction, it will keep oscillating back and forth. Now we have to find out whether this oscillation is SHM or not. The condition for this oscillation being SHM is this restoring force should be proportional to the displacement. So when we displace this thing by a small amount x, then the electric field due to 1 will change as lambda by 2 pi epsilon naught into 1 by the distance. When it's displaced right by a small amount x, then the displacement would have increased by L plus x, and the electric field due to 2, the distance has decreased to L minus x. And the direction of electric field due to 2 is towards left, so it's a minus I cap direction, so that's why this minus sign is being put. Electric field is a vector, so you have to take care of the direction by this sign. So the net electric field is E1 plus E2. So if you add these two, we'll get 1 by L plus x minus 1 by L minus x. So that will give minus 2x divided by L square minus x square. And since this distance is very, very small, x square can be neglected. So this will become proportional to minus x. So the restoring, since the net force is proportional to minus x, the restoring force, which is the charge q to this net electric field, that is also proportional to minus x. So this is the condition for SHM, where the restoring force is proportional to the displacement, and the direction of the restoring force is towards the equivalent position. Here the displacement is towards right, and the restoring force is in the negative direction. That means it's towards the equivalent position. So this will execute a SHM motion. But minus Q, initially the electric field here is 0 because E1 and E2 magnitude are same and the directions are opposite. But suppose if we try to displace this minus Q towards right little bit, now since it is moving closer to 2, E2 will increase and E1 will decrease, and E2 is towards right, so there will be a net force towards right. So this force will still take it further away from the initial position. So small displacement towards right will take it further from this initial position. So it will continue to move in the direction of the displacement, initial displacement. Similarly, if I try to displace this thing little bit towards left, since it's moving closer to 1, the magnitude of electric field due to 1 will increase and E2 will decrease because it's moving away from 2. So there will be a net force towards left. So this will try to take this minus Q away from this initial position. So the charge minus Q, if you give an initial displacement towards left, it will continue to move in the same direction. So option A says both will execute SHM. That's not true. Option B, both will execute, continue to move in the direction of the displacement. That's not true. Option C, plus Q will execute SHM and minus Q continues moving in the direction of displacement. So this is correct answer. Option D, minus Q will SHM. So option D is not correct. But suppose if Q is negative, then option D is true and option C is not correct. They have not mentioned in the question that Q is positive, but if that ambiguity is taken into account, then both these options are possible depending on whether Q is positive or negative. To summarize, motion of a charged particle in uniform electric field is similar to that of a projectile motion. The x motion is the initial velocity into time t. X motion has got no acceleration, it's a uniform velocity motion. The y motion is half at square. Here we are assuming that the initial velocity in the y direction is 0. So it's half acceleration, which is e by m into time square. And the path is a parabola. If you eliminate t between these two equations, we get the relation between x and y for the path. So y goes as x square and minus x square, coefficient is negative. So it will be inverted parabola. I also take doubt solving sessions for physics and math subjects of JEE and NEET. So if you're interested, you can contact me. This is my WhatsApp number. And fees is nominal. First class is free. Description box has got links and timestamps. You can watch parts of video that you find interesting.